Hello, everyone. Good morning. Welcome to the second OpenCoast course. My name is Anabela Oliveira, and given the pandemic context, we have recorded all lectures, so you have a better experience. So my recommendation right now is that during the question periods, you can ask questions in this, by raising your hand. But my recommendation for a smoother streaming is to put your questions in the chat, and this way we can answer during the projection of the movies. I hope you enjoy the tutorials, and we are going to start now with the first part. Thank you. Welcome to the second OpenCoast tutorial. My name is Anabela Oliveira, and I'm a researcher at UNEC, and I'll be leading the course today. So we will start with what is OpenCoast and what are the goals for today's training. OpenCoast is one of the thematic services from the European Open Science Cloud Hub project. It is provided by a consortium composed by UNEC, LIT, CNRS La Rochelle, and the University of Cantabria. So what are the goals for today's training? We are going to reintroduce or introduce OpenCoast, whether we have attended the first course or not, which is an innovative and free platform to generate on-demand forecasts. We would like to, with this course, to empower you, potential user, by providing an overview of the relevant concepts, the capacities of this service, and what are the circulation options. Finally, we would like to minimize your learning curve by providing step-by-step demos on each of your Today, we are going to have an overview of the background coastal topics, and tomorrow we are going to have demos for the several options of OpenCoast. Then in day 3, we are going to have for the first time an OpenCoast developers training for the people that want to install OpenCoast at their own infrastructures. Remember that the hours in these timetables are CET for -1 hour for Portugal. So what is the detailed program for today? We will start with the first tutorial on coastal processes given by Sonia Castaneda and Fernando Mendes from the University of Cantabria. Then we have a tutorial on the baroclinic circulation, an overview of the 3D coastal processes by my colleague Marta Rodrigues from UNEC. Finally, and before the break, we will have the understanding and using model schism given by Professor Javier Bertin and Laura Lavaux from the CNRS La Rochelle University. After a short break, only 15 minutes, we come back and have the lesson on WWM and its coupling with schism, given again by Javier Bertin and Laura Lavaux. Finally, we have a very important lesson for the generation of the finite element grids that you need to use OpenCoast, given my colleague André Fortunato from UNEC. And this will close the work for today. And again, remember, hours are CET -1 hour in Portugal. A couple of rules on how this is going to operate. We are going to allow for questions from all the attendees that want to pose questions, but there are some ways to do that. We can have questions during the question periods, and people have to raise their hand in Zoom if you have a question, and then wait for the moderator to give you the stand for you to speak up your question. Or during the sessions, you can put questions in the chat, and we will be able to answer those also again during the chat. If you have enough time, we can bring some of the chat questions to the open part. Finally, as always, for a smooth and well-conducted tutorial, please avoid being late to the sessions and remain silent during the sessions and keep your phone in silent mode. And don't forget, we are going to be around during the breaks and at the end of the days to ask all the questions that you have on OpenCoast. Well, thank you for your attention. Enjoy the tutorial. And if you have any questions in the future, here is my email, and I will be glad to help you in any way I can.
This presentation provides a short introduction to coastal hydrodynamic processes. In Chapter 1, we are going to see an overview of wind waves in the ocean. Wind waves in the ocean are random and irregular. To study the behavior and characteristics of ocean surface oscillations, we usually analyze them by means of mathematical models that describe homogeneous properties of the energy in the ocean in the time domain, frequency domain, or statistical domain. The interval of time in which we can assume that the energy of the free surface oscillation at a particular location of the ocean is constant is defined as a sea state. How are waves generated? Wind transfers energy to the ocean surface, generating waves. The wind blows in an area defined as a fetch. At the beginning of a storm, waves have little energy, a short period and a low height. As the storm continues, the waves transfer energy from the short periods to larger wave periods. The longer the duration of the storm and the larger the fetch, the greater the wave height and the wave period, until it reaches a state of equilibrium. The associated sea state is defined as wind C. These progressive waves abandon the area of generation, propagating in the ocean according to each wave's celerity. Waves with a longer period propagate faster than short period waves, thus filtering and cleaning the sea state. The associated sea state is defined as swell. At a particular location in the ocean, the random and irregular behavior of the sea state can be defined mathematically as a linear summation of many harmonic or sinusoidal waves of different direction, frequency, and height. We can group the amount of energy into different directional sectors and frequency bands, which is proportional to the square of the wave height. By doing this, we are defining the directional spectra. Therefore, the shape of the directional spectra defines the characteristics of the wave field. And this is the function that will allow us to analyze its properties by means of simple aggregated parameters, or will allow us to understand the propagation of energy from one point to another in the ocean. Integrating the directional spectrum, we can obtain very important parameters that describe the sea state, such as the significant wave height, the mean wave period, and the mean wave direction. The peakness and the directional spreading of the directional spectra also help us to identify if the sea state is a wind sea, large directional spreading, or a swell, high peakness value, that has abandoned the area of generation. The wind sea reaching this beach is characterized by short-crested wave length, waves with different wave direction and period. On the other hand, a swell reaching the same beach is characterized by long-crested, well-organized, clean waves, in terms of not having high frequencies. Consequently, the surf zone hydrodynamics of a wind sea or a swell are totally different. In nature, often free surface at a particular point in the ocean is the combination of a wind sea component plus one or more swell systems, as we can see in this sketch of the Dutch coast. Here we have the local wind sea plus the swell that was generated 2 days earlier in the northern part of the North Sea. It is essential to consider this aspect of multimodal directional spectra in the downscaling of wave propagation and generation models. The boundary conditions of a higher resolution wave generation model need to be defined in terms of the spatial and temporal variability of the directional spectra, as we can see in this example. In many cases and many offshore and coastal applications, it is common practice to reduce the complexity of all the degrees of freedom of a directional spectra, obtaining a parameterization of the directional spectra. This is usually done by splitting the directional spectra into the product of a frequency spectrum and a directional spreading equation. The John-Swapp frequency spectrum is defined in terms of the significant wave height, the peak period, and a peak enhancement factor named gamma. directional spreading is usually defined with cosine power functions as seen in the example. Depending on the values of the parameters that describe frequency dispersion and directional spreading, we can obtain different possible and plausible free surface wave fields. When the directional spreading, sigma, is very small and the gamma is very large, we create a swell. Or on the other hand, when the directional spreading is large and the gamma is small, we have wind seas. So, for a particular directional spectra, by creating random phases for the harmonics, we can define an infinite number of possible waves with the same aggregated parameters: the significant wave height, the peak period, the mean direction, gamma and sigma. On the left, you can see a wind sea characterized by its chaotic behavior, with waves of different frequencies and directions. On the right, you can see a swell, where the waves are sorted, clean, with a clear frequency and direction, similar to a monochromatic wave train. But how can we measure wave heights at a particular point in the ocean? There are many different devices, but one of the most widely used ones is a buoy that captures the vertical oscillation of the free surface of the ocean over time, therefore obtaining wave parameters, such as the locations of the crests, the troughs, and the wave height and wave period. During a real sea state of 30 minutes, we can see that there are different wave heights, a series of small waves, large waves, and so on. If during this sea state we collect all the observations of wave height and group them into classes, we obtain the histogram, or empirical probability density function of wave height. As seen, in this particular sea state, the average wave height is about 2 to 2.5 meters, and the larger wave heights are about 5 meters. The best mathematical model for characterizing wave height distribution is the Rayleigh distribution. This is a distribution with a mode, only positive values, and skewed on the right-hand side. The only parameter of this distribution is HRMS, the root mean square wave height. Therefore, by just knowing this parameter, we can estimate all the possible wave height statistics. Nowadays, there are other ways of measuring waves. Observations from satellites provide a unique and very accurate worldwide database of wave heights that is very useful for validating numerical models. In Chapter 2, we will briefly analyze wave transformation. When waves propagate towards the coast, they suffer different wave transformation processes that modify the wave height and the wave direction. These modifications in the wave field are key to understanding many different coastal processes, such as coastal inundation, beach morphology, or cliff erosion. They must also be taken into account when designing coastal structures. Reflection occurs when a wave train hits an obstacle, a cliff in this case. Refraction occurs when a wave train bends or rotates due to changes in the bathymetry. Shoaling affects the wave train, reducing the wave celerity and increasing the wave height. Diffraction occurs in the leeward part of an obstacle, producing a reduction in wave height and the generation of concentric wave trains. Braking is the last wave transformation process. As seen earlier, the ocean free surface can be decomposed into a number of harmonic waves with different directions, frequencies, and amplitudes. In the linear wave theory, we can assume that the linear superposition of monochromatic wave trains is valid. Therefore, we can analyze the kinematic and dynamic properties of a progressive monochromatic wave train. So let's assume that we have a linear wave train propagating in the positive axis with a celerity c. Waves propagate in a water depth h over a still water level. The vertical distance between a crest and a trough is the wave height, capital H. The horizontal distance between two crests is the wave length, capital L. In the time domain, the distance between two crests is the wave period, capital T. As we are dealing with sinusoidal waves, we can define two important parameters, such as the wave number, k equals 2 pi over L, and the angular wave frequency, omega equals 2 pi over T. Besides, the wave celerity is defined as k equals L over T, or omega over k. So in one period, the wave propagates one wavelength. Mathematically, the expression of the free surface of a wave train propagating in the positive axis is eta equals h over 2 times the cosine of kx minus omega t, where kx minus omega t is the phase. More generically, a progressive wave train propagating obliquely with an angle of theta with respect to the x-axis is defined as eta equals h over 2 times the cosine of kx times cos theta plus ky times sin theta minus omega t. Once we have the wave that propagates in a water depth h with a wave period t and a wavelength L, we can define a dimensionless parameter, relative water depth, h over L, that informs us about how the wave transmits information in vertical. So, waves in which h over L is larger than a half propagate in deep water, and their effect does not reach the bottom. When h over L is between a half and 1/20th, waves propagate in intermediate water depth. In this case, their effect reaches the bottom with a vertical damping. Finally, when h over L is smaller than 1/20th, waves propagate in shallow water. The effect reaches the bottom homogeneously. These waves are named long waves and will be analysed in the following section. So, a wave train that propagates from deep water to shallow water begins to feel the bottom when h over L is below 0.5. The effects are a reduction in wave celerity and group celerity, which is the celerity of the wave energy. These changes in celerity and group celerity are responsible for two wave transformation processes, shoaling and refraction. Starting with shoaling, let's assume that we have a wave train that propagates perpendicular to a bathymetry with parallel isobaths. During propagation, and assuming that there is no reflection and no loss of energy, the magnitude energy flux is constant. Energy flux, capital F, is defined as the product of the energy, capital E, and the group celerity, Cg. As seen, wave energy is proportional to the square of the wave height. When propagating to shallower water, the wave train reduces its group celerity, and therefore, as the energy flux between deep water and a point in shallow water is constant, it produces a sudden increase in the wave height close to the beach. In order to see an example of shoaling, let's go to Tahiti, to Te Haupu. In this coastal area, there is an abrupt change in water depth due to the morphology of the coral reef. This fact induces prominent and fast shoaling that in most cases ends with the wave breaking on the reef. For example, to have a rough order of magnitude of this process, a wave train with a wave height of 2 meters and a wave period of 20 seconds can be transformed into a wave train of more than 6 meters, which results in a shoaling coefficient of more than 3 units. In most cases, waves propagate with an angle of incidence with respect to the perpendicular to the isobaths. In this case, the magnitude that is conservative is also the wave energy flux between orthogonals. During propagation, the rotational of the wave number is 0, meaning that wave rays bend when they approach the coast, trying to be perpendicular to the isobaths. Therefore, the wave direction rotates from deep water to shallow water. For parallel isobaths, This equation is named Snell's law, meaning that the sine of the angle of incidence divided by the celerity is constant during propagation. Let's now go to the coast of Namibia, in which swells hit the coast with a very oblique angle of incidence. Namibia. This wave-breaking pattern produced by refraction is responsible for a longitudinal current, generating a very active dynamic system from a morphodynamic point of view. When waves approach a headland, the refraction of the wave rays produces a pattern that tries to focus wave rays on the headland, inducing a local increase in wave energy and diverging in the bay areas, inducing a reduction in wave energy. Let's now look at an example in Southern California. In this picture, we can clearly see that the waves in the bay area are very small in comparison with the waves close to the headland. Diffraction occurs in the leeward part of an obstacle, such as a headland, producing a reduction in wave height and the generation of concentric wave trains. The obstacle can be natural, headland, capes, islands, or man-made, such as a breakwater. In a real environment, as in this complex bathymetry, all of these processes occur together: shoaling, refraction, reflection, diffraction, breaking. Nowadays, there are high-resolution models, grid cells of 1 or 2 meters, that are able to solve all these processes. In this animation, we can see the evolution of the free surface associated with the propagation of a directional wave spectra from deep water towards the coast. Chapter 3 concerns long waves. In this chapter, we're going to talk about long waves. First of all, I will give you some definitions, then we will review the main types of long waves that we can find at the coast. I will show you why long waves are important and explain their contribution to coastal processes. We will finish with the governing equations for these waves. Here you can see the main characteristics that define a long wave. They are waves with long periods and wavelengths, so they fulfill the relationship of shallow water. According to that, their celerity only depends on the depth. Notice that waves with long periods are shallow water waves, even in the deep ocean. As an example, let's see the astronomical tide, with a typical period of 12 hours, propagating over a depth of 3,000 meters. If we calculate the relative depth, we will see that even this huge depth is shallow water for this kind of long wave. Let's see some definitions and the coordinate system that we're going to use. All the variables refer to the mean sea level. That is an average level used as the vertical datum. The amplitude of a wave is the vertical distance between the mean sea level and a crest, or the mean sea level and a trough. The free surface elevation is the vertical distance between the mean sea level and the surface of the wave. The water depth is the vertical distance between the mean sea level and the ocean bottom. The wavelength of a wave is the distance from one crest to the next one. And finally, the wave period is the time it takes 2 successive wave crests to pass a fixed point. Now we are ready to see what long waves we can find at the coast. In the following slides, we will take a quick look at each one of these long waves. If you want to know more about them, you can consult the bibliography provided at the end of the presentation. Let's start with the astronomical tide. Here you have a definition: the periodic rise and fall in the level of the water in oceans and seas as a result of gravitational attraction of the sun and moon. The moon induces the strongest effect on the tides due to its relative closeness to the Earth. In the figure, you can see a sea level record with two important parameters: the tidal period and the tidal range. Both of them depend on the relative position of the moon and the sun with respect to the Earth, and they are different from location to location. With regard to the period, tides can be semi-diurnal with 2 high tides and 2 low tides per day, or diurnal with 1 high tide and 1 low tide per day. Tidal range can vary considerably depending on the location. Whilst in the ocean it reaches a maximum value of 50 centimeters, it is greatly amplified on the continental shelf, in the coastal boundary, and in estuaries. The figure shows a sea level record for almost 1 month, where we can see spring tides and neap tides. Spring tides occur during full or new moons, when the Earth, Sun and Moon are almost aligned, and the average tidal ranges are slightly larger. This occurs twice a month. 7 days after a spring tide, the Sun and the Moon are at right angles to each other. This produces moderate tides known as neap tides, meaning that high tides are a little lower and low tides are a little higher than average. Neap tides occur during the first and third quarter moons. Astronomical tides are often the defining water motion in coastal areas. Tides cause large-scale current patterns, sometimes with large velocities. For example, in the Bay of Fundy, we can find velocities of up to 5 meters per second, and they directly affect coastal morphology, navigation, fisheries, habitat, and recreational activity. Today, in contrast to the majority of coastal processes, tides can be predicted with a very good accuracy, for as many as 200 years in advance. A tide gauge is a device for measuring sea level. Tides can be predicted by analyzing long-term tidal records of at least 2 years using the harmonic method. The observed tide can be regarded as the sum of a number of constituent sinusoidal waves, each possessing a defined amplitude and period. The period corresponds with the period of one of the relative astronomical motions between the Earth, Sun, and Moon. The amplitude and phase of each particular constituent is unique to each location. The nature of the tide at a given location depends on which of the constituents is dominant. Here you have a table of principal harmonic constituents. Note that the period of each harmonic constituent is known because, as I said before, the different periods represent astronomical motions between the Earth, Moon and Sun. So, if you know the tide at a specific location, and you are lucky and there is a tide gauge at the point of interest, you can apply harmonic analysis and obtain a sea level prediction for the desired time period. But if you need to calculate tide sea level and currents in an area, you will have to use numerical modelling and propagate the tide. Both approaches are complementary because the sea level record can be used as a boundary condition and/or validation data. Moving on to the next type of long wave, we have the storm surge, that is the rise in water level on an open coast as a result of the combined impact of the atmospheric pressure gradients, which produce what is called the inverse barometer effect, and the wind stress on the water surface. Storms occur typically in winter, forced by extratropical storms, and in summer to early autumn by tropical cyclones. They have the greatest impact in shallow seas and low-lying coastal areas, where they may be very destructive. An extreme example of storm surge is that produced by hurricanes. In the image, you can see Hurricane Katrina in 2005, which produced storm surges higher than 7 meters on the Gulf Coast of the United States. Seiches are another kind of long wave. A seiche is the free oscillation of a water body. For a seiche to occur, we need a body of water that has its natural period of oscillation and an external perturbation or wave whose period matches the basin's period. The external perturbation is most often a meteorological effect, such as wind and atmospheric pressure variations, infragravity waves, seismic activity, or tsunamis. The period of seiche oscillation is typically within the range of 2 to 40 minutes. It is important to carry out field investigations to establish if there is a seiche present in a given area. And if so, take this into account in the layout of the port to avoid harbour resonance. In the images you can see the port of Ciudadela on the island of Menorca before and during an episode of resonance. In this case, the SACE has been produced by atmospheric pressure variations. Now let's look at infragravity waves. These are ocean surface waves with a typical period of 30 to 300 seconds. Infragravity waves are indirectly formed by the wind. Their creation is linked to the presence of short wave groups, which are formed due to the superposition of two different shortwave trains with wavelengths and frequencies that are very similar. Why are these important to the coast? They account for 20 to 60% of offshore energy. They dominate shoreline oscillations and run-up. They are reflected at the shoreline. They contribute to surf zone circulation, and they can produce harbour resonance. The last type of long wave that I am going to show you is a tsunami. A tsunami is a series of travelling waves of extremely long length and period, usually generated by disturbances associated with earthquakes occurring below or near the ocean floor. The speed of a tsunami's propagation is directly related to the depth of the water over which the wave passes. This figure shows how a tsunami is formed. First of all, there is vertical movement of the ocean floor that displaces the water column. It produces a series of waves which travel to the coast, where the energy compresses due to shallow water and the wave height increases. It is very difficult to attribute a probability to tsunami impact on the coast. There are long intervals between events, so we need data which covers hundreds of years. Because of the lack of long-term systemic observations, we can only obtain approximate recurrence intervals. Following this quick review, you can understand why long waves need to be studied. However, let me give you some reasons why these waves are so important. Long waves are the main components of sea level. They define the hydrodynamics of estuaries and lagoons. We have seen that they have to be taken into account when designing a harbour due to resonance issues, and long wave-induced currents need to be assessed in order to study water quality and coastal sediment transport. I am now going to give you some examples. This figure shows the main components of sea level at the coast. We have the contributions of the astronomical tide and storm surge, both of which are long waves. We can see the run-up, which is the result of the wave breaking effect, and also includes the surf beat, which is the contribution of infragravity waves. Here are two examples of how important it is to know the sea level in order to answer questions related to coastal management. What is the flooding risk? How large must these concrete cubes be for the breakwater to be stable? This depends on wave height and sea level. Long waves are usually the main drivers in estuaries and lagoons. In the figure, you can see the ebb currents in a tide-dominated estuary, calculated using a numerical model that propagates long waves. Note that there are currents of up to 1 meter per second at the narrowest parts of the bay. Furthermore, estimating long wave-induced currents is very important for water quality studies, as you can see in the figure, where the upstream transport of a salt wedge is being estimated using numerical modeling. Next, I will show you the equations that we have to apply to calculate sea level and currents due to long waves. We start with the conservation equations for an incompressible fluid, the continuity equation, and the three equations of conservation of momentum. Here is one of them, the equation in the x direction. The next step is to apply the long wave hypothesis, which establishes that as we are dealing with waves whose length is much greater than the depth, the vertical accelerations can be neglected. After this, we have this equation in the z direction, which means that pressure under long waves is hydrostatic. Finally, these are the 3D equations for long waves, the continuity equation and the equations of conservation of momentum in the x direction and in the y direction. An example of a case where you should apply these equations is wind-induced flow. Wind blowing over a free surface will produce wind setup and vertical current profiles. However, there are cases where we know that the horizontal velocity is not a function of depth. For example, when we want to calculate astronomical tide currents in a well-mixed estuary. In these cases, we can integrate the governing equations over the water depth and obtain the 2D shallow water equations. Looking at the equation of motion in the x direction on the left-hand side, we have the acceleration terms. and on the right-hand side, we have terms representing the effect of the Earth's rotation. Here you have the sea level gradients and the density gradients. Here you have the terms representing the atmospheric pressure gradients and wind stress, which, remember, are the forcings of the storm surge. Finally, this term represents the bottom friction, and these are terms standing for the turbulence. In these equations, h is the total water depth, and u and v are the depth integrated velocities. To sum up, here are just some ideas to keep in mind. Long waves are shallow water waves with long periods and lengths. The long wave hypothesis is that pressure under long waves is hydrostatic. They are the main components of sea level. They are responsible for harbor resonance, and they can induce high currents. Finally, here you have a bibliography for you to learn more about long waves. You can see a very interesting video about tides at this link. Finally, I would like to thank the ICT department at the University of Cantabria for its technical support in making this video, and the European project EOSC-hub for its funding.
Hi, good morning. So this is Fernando Mendez and Sonia Castanedo. We are both professors of coastal engineering at University of Cantabria, and what you have seen is a very brief overview of coastal hydrodynamic processes involving wind waves, wave transformation processes, and long waves that are essential for forecasting coastal flooding and coastal currents. So I guess now it's time for questions. So if you have any question in the following minutes, so we are happy to try to answer them.
Can we get some links in the chat to know more about these points you explained in this brief course?
Okay, so if there is no questions, you can storage all your questions to the end of the session, and you can ask at the end. Okay, thank you.
Hello, my name is Marta Rodrigues. In this lecture, we will talk about baroclinic circulation in coastal areas. The lecture will start with a brief overview about barotropic and baroclinic conditions and the governing equations for coastal circulation. Then, we will talk about the influence of baroclinic effects in coastal dynamics and processes that affect stratification in coastal areas. Finally, we will talk about three-dimensional modeling in coastal areas. So, let's start by barotropic and baroclinic conditions. In barotropic conditions, the isobaric surfaces, the surface with constant pressure, follow the sea surface. In this case, isobaric and isopycnal surfaces with constant density are parallel, as shown in the left. The barotropic pressure gradient is thus the part of the pressure gradient that is due to the slope in sea surface. In baroclinic conditions, the surfaces of constant density intersect the surfaces of constant pressure, as shown in the right, and the density field can modify the pressure gradient. In this case, we have the baroclinic pressure gradient. Regarding the governing equations, coastal circulation is described with Navier-Stokes equations. Here we focus in standard Navier-Stokes equations with hydrostatic and Boussinesq approximations, including the momentum equation and the continuity equation. The momentum equations relates the sum of the forces acting on an element of a fluid to its acceleration. It considers changes in the free surface elevation, the vertical and the horizontal viscosity, and other forces such as the Coriolis effect, the baroclinic term, the atmospheric pressure. The continuity equation deals with the volume conservation. For a given volume, it states that the changes in the free surface elevation must be explained by the net flux in that volume. Additional equations are required. In particular, we need to solve the transport equations for salt and temperature to determine the density. We also need to determine the vertical eddy viscosity coefficient through a turbulence closure scheme. In the next slides, we will see some examples of the importance of baroclinic effects in coastal dynamics. Baroclinic effects can influence the estuarine circulation in different ways. Cao and Olabarrieta explore these effects using numerical modeling. In strongly stratified estuaries, baroclinic effects result in a two-way flow. Residual velocities can be directed upstream at the bottom and downstream at the surface. In well-mixed estuaries, surface water goes upstream and bottom water goes downstream as a compensating flow, both in barotropic and baroclinic conditions. In partial mixed estuaries, baroclinic effects generate a triple directional estuarine circulation: a downstream flow below the tidal wave through, an upstream flow close to the bottom, and an upstream flow between the wave crest and through. Baroclinic effects can also have a significant influence in storm surges. In a modeling study of storm surges in Delaware Bay, Ye et al. Found that baroclinic effects are important to adequately capture the adjustment processes following the main storm. The figure presents the differences of sea surface height and sea surface slope for 3D baroclinic, 3D barotropic, and 2D applications. The largest differences in elevation were found during the post-storm adjustment period, as you can see in the bottom figure, and the processes were better captured by the baroclinic model. Baroclinic effects may also be important on the flushing capacity of estuaries. Looking at the bottom figure, we can see some results of the study of Du et al. In Mobile Bay. They found that for low to moderate river flows, the influence of the baroclinic effects was of the same order of magnitude of the influence of the river discharge. The importance of this effect decreases with the increasing of the river flow. For low to moderate river flows, their results suggest that the estimated flushing times were about half of the previous estimations based only on barotropic processes. The next slides will focus on processes that affect stratification. Stratification is a measure of how much the density of the water changes, and is caused by difference in temperature or salinity or both. Stratification can change in time, as you can see in the figure. The variations in time depend on the balance between the forcing mechanisms that can promote stratification, or on the contrary, that can promote mixing. Several processes can affect stratification, including the freshwater runoff, the heating and cooling at the surface caused, for instance, for heat exchanges, the precipitation evaporation, and also surface and bottom stresses, such as the winds or the waves. The freshwater runoff affects salinity dynamics and, consequently, stratification. The figure shows a scheme of how river flows can affect estuarine salinity stratification. S1 to S5 are salinity contours along the estuary. In general, we can see that the larger the river flow is, the stronger the stratification will be, as shown in the bottom figure. Here is another example in coastal fronts. Fronts are regions of intensified horizontal gradients which occur widely in shelf seas and estuaries. Here you can see a figure of the mechanism by which cooling creates density-compensated submesoscale fronts and cold sea surface temperatures filaments. In a salinity stratified upper ocean, salinity fronts cause restratification and shallowing of the surface mixing layer. Cooling occurs in the shallow, most stratified surface mixing layer, creating a larger drop in the sea surface temperature along salinity stratified fronts. Sea surface temperature and sea surface salinity become correlated, compensating their effects on density. Wind can also play an important role in stratification. Observations from the York River estuary show that the long-channel wind plays a dominant role in governing the estuarine exchange flow and the corresponding increase or decrease in vertical density stratification. Down estuary winds enhance the tidally average vertical shear, which interacts with the long-channel density gradient to increase vertical stratification. Up estuary winds tend to reduce or even reverse the vertical shear, reducing vertical stratification. The last example is about Ekman transport, upwelling and stratification. The Ekman current is a surface current that develops from steady wind at ocean surface. This current develops at an angle of 45 degrees from the wind at the surface and forms a spiral in the water column, as you can see in the figure. Coastal upwelling occurs when the Ekman transport moves surface waters away from the coast, as you can see in the bottom figure. Based on field observations in Monterey Bay, Walter et al. Showed that the wind modifies the offshore stratification and the thermocline depth. During strong upwelling conditions, which in the top figure are represented by positive values, the offshore thermocline shows toward the surface. During weak upwelling favorable conditions, the offshore thermocline deepens. Finally, we will talk about three-dimensional modeling in coastal areas. There are several numerical models for the simulation of the three-dimensional coastal circulation. Here, you can see a list of some of the most used models. These models solve the governing equations presented before. With the exception of Mike 3, all of these models are open-source community models. So, how do we set up a numerical model? First, we need to specify the model domain, horizontal and vertical grids. We also need to specify the boundary conditions, the model parameters such as the time step or the turbulence closure scheme, and we also need to specify the initial conditions for the variables. Then, the model application requires both calibration and validation procedures to assess the model performances. Since the focus of this lecture is 3D coastal processes, further details about the vertical grid will be discussed in the next slides. So, how does the vertical grid affect the model results? Three vertical coordinate systems are commonly discussed, with advantages and disadvantages among them. Geopotential Z coordinates present the simplest numerical discretization. However, this vertical coordinate system can lead to artificial staircases, and it's also difficult to represent the bottom topography and the moving free surfaces. Terrain following coordinates, sigma or S, allow a smooth representation of the bottom topography. However, there are some difficulties to accurately represent the horizontal pressure gradient in steep slopes. Isopycnal coordinates are natural for large-scale ocean simulations. However, they are problematic in well-mixed zones. To overcome some of the referred limitations, some models use hybrid coordinate systems, combining, for instance, Z coordinates with terrain following coordinates, as you can see here in the figure, where S coordinates are used in the shallow zone and Z coordinates, S and Z coordinates are used in the deeper zone. Some examples of the influence of the vertical grid setup on the model results will be shown in the next slides. Here you can see an example of how the vertical grids affect the vertical velocity profiles, with a better approach of the analytical solution when higher resolution vertical grids are used. In this slide, salinity profiles are shown for the Columbia River using different vertical grids. The number of layers in the vertical grids increase from the top to the bottom. Results show a significant influence of the vertical grid setup in the freshwater plume representation. In the next slide, we can see the effect of the vertical grid in the temperature simulation. Temperature vertical profiles in the Lake Mendota are presented for simulations with different vertical grids. Observations data are presented on top left for comparison. Again, we can see that the setup of the vertical grid plays an important role in the model performance. There is one relevant issue when establishing the vertical grid, which is the computational times. As an increased number of vertical levels also increase the computational times, and a balance may be required. Finally, here is an example of a three-dimensional modeling application in an estuary, the Tagus estuary. This is one of the largest estuaries in Europe that connects to the Atlantic Ocean and also has an important freshwater input from the Tagus River. The model was implemented using schism and for the horizontal domain, a grid with about 83,000 nodes was used. Two vertical grids, one hybrid grid with 39 levels and one grid using LSC squared coordinates were tested. Here are some results for simulations performed for a period of large that promotes stratification. And you can see on the top, you can see the observations and then the results for the two grids. And you can see some differences regarding the stratification with the LSC squared grid leading to slightly better results. So this is the end of this lecture. Thank you for your attention.
Okay, so good morning, everyone. Thank you. So this lecture was about 3D baroclinic processes in coastal areas, and we now have a couple of minutes for some questions. So if you have any questions, please do so. Okay, so it seems like we don't have any questions. So if meanwhile you have any questions, you can put that question in the chat or leave it for the end of the morning. Thank you.
Good morning, everyone. My name is Xavier Bertin. I am a researcher at the lab Liens, a joint research unit between the University of La Rochelle, France, and our National Research Center. I am leading a team named Physical Dynamics of Coastal Zones, who is taking part in the development of schism, namely with respect to wave current interactions, sediment transport, and morphodynamics.
Hello everyone, I'm Laura Lavo and I worked on the development of OpenCoasts this year. Now I'm doing a PhD on storm surges supervised by Xavier in La Rochelle.
Here is a plan of our course. We will start with a brief introduction and follow on with a physical formulation of schism, its numerical formulation, and some guidelines to use it. Introduction. Schism stands for Semi-Implicit Cross-Scale Hydroscience Integrated System Model. Schism is a 3D seamless cross-scale model for hydrodynamics and ecosystem dynamics. It is a derivative from the original SELF model implemented by Dr. Zhang from the Virginia Institute of Marine Science and other developers from all around the world. Schism can be applied to a large range of scientific problems such as storm surges and flooding, wave current interactions, baroclinic simulations, sediment transport, and morphodynamics, ecology, water quality, and oil spills. Schism has really cross-scale capabilities and can be applied without any nesting from the continental shelf to the whole watershed. Here I will present you its main features. The horizontal space is discretized using unstructured grids, which can combine triangles and quadrangles. The vertical discretization can use SZ or LSC square coordinates. 1D, 2DH, 2DV, and 3D can be combined in one single run. Cartesian or geographic coordinates can be used. The numerical algorithm combines finite element, finite volume, a Lagrangian method for the momentum advection, and a semi-implicit time stepping, which makes this model very efficient. No bathymetric smoothing is needed, and advanced numerical methods for wetting and drying are available. Chapter 1. Physical formulation. Schism solves the 3D Navier-Stokes equation under hydrostatic and Boussinesq approximations. Here are the continuity equations in 3D and 2DH, where U corresponds to the horizontal velocity, W the vertical velocity, eta the free surface elevation, and H is the bathymetry. The total water depth equal eta plus H. Here are the momentum equations, where G grad of eta represents the barotropic pressure gradient, and the term with mu represents the vertical mixing. F is the sum of the sources and sink of momentum and includes, from left to right, the Coriolis acceleration, the tidal potential, the atmospheric pressure gradient, the horizontal mixing, the forces due to short waves, and the baroclinic pressure terms in baroclinic mode. Schism also includes transport equations, where C is the concentration of the tracer, K is the vertical eddy diffusivity, and F are the sources and sink of tracers. An equation of state is also solved. With respect to the vertical boundary conditions for the momentum equations, the surface and bottom stresses are imposed at the surface and at the bottom respectively. For the surface stress, several formulations are available. First, we can use the bulk formula of Pond and Picard. Second, the aerodynamic module of Zeng can be used. And finally, several wave-dependent approaches are available, but these are still under development in our team. For the bottom stress, the approach of Bloomberg and Mellor is employed, where Z0 corresponds to the roughness length, which can account for bed forms in sediment transport simulations. Wave-dependent approaches, such as, according to Soulsby or Grant and Madsen, are also available. When the horizontal velocity is not strongly sheared, for instance in shallow waters outside the surf zones, where baroclinic effects are negligible, or when there is no vertical circulation, such as in bended channels, then the model can be used in depth-integrated mode. In this case, bottom friction is represented through a Manning approach, where n is a Manning coefficient. In 3D, the equations must be closed by turbulence closure for the viscosity or diffusivity. The generic length scale model of Umlauf and Burchard is employed. The additional turbulence produced by waves in the near shore is also implemented, although it is still under development in our team and will deserve more verifications. Thank you for your attention.
I will now describe the numerical formulation of the model schism. First, we focus on the spatial discretization of the computational domain. Schism is a finite element model. It is therefore implemented with unstructured grids in the horizontal dimension and flexible vertical coordinate systems in the vertical dimension. Regarding the unstructured grid, they combine triangular and quad elements to take advantage of both of them: the boundary fitting of triangles, and the efficiency of quads in resolving features like channels. In the vertical dimension, two types of coordinate systems are available: the hybrid SD grid and the LSC square grid. The first vertical coordinate system uses terrain following S coordinates and chef Z coordinates. They are separated by the HS depths. Chef Z layers are optional, which means that a pure S grid is an accepted configuration which can be set by defining an HS greater than the maximum depth of the grid. The transformation from S to Z is adjusted by constant θ b and θ f that control the vertical resolution near the bottom and surface. When θ b tends to 0, only the surface is resolved. When it tends to 1, both are resolved. When θ f is much greater than 1, more resolution is skewed towards the boundaries. These are some configurations with various θ f and θ b. In the first case, for example, θ f is close to 0 and there is no θ b, which means that the user doesn't want more resolution toward the boundaries. You can see on this figure chef Z cells near the bottom. The second type of vertical system available is the LSC square grid, which means localized sigma coordinate chef cells. Each grid node has its own number of levels, and the mismatch of number of levels between adjacent nodes is corrected with chef cells near the bottom. This vertical system can be designed by creating a master grid at selected reference steps and then using it to template the local Z coordinates at the grid nodes. It allows a faithful representation of the bathymetry, avoiding any pretreatment on it, but it requires some experience. For beginners, it is more convenient to start with the SD grid. Now we can focus on the basic 3D computational unit of a domain. For both types of vertical system, the basic unit is a triangular or vertical prism. All variables are spread at different locations on this unit. The surface elevations are defined at the nodes, the horizontal velocities are defined at the side centers, and the vertical ones are defined at the element centers. The tracer concentration is defined at the prism center. At the end of each computational time step, the free surface movement is taken in account by updating the vertical levels. Over large domain, distances in map projection are not conserved. Therefore, it's preferable to use spherical coordinates that are longitude and latitude. Instead of adapting this equation to the longitude and latitude coordinates as is usually done, another approach proposed by Comblain et al. In 2009 is used. Multiple local frames at different locations are combined, and the model solves the equations without changing them. The combination of a LSC square grid and an horizontal mixed element grid provides the user with a high flexibility for various applications. For example, on this figure, the deeper part of the domain is treated with a 3D configuration, but with fewer levels in the shallower parts. Some waters, sufficiently shallow, are discretized with one vertical layer, which is a 2D edge configuration. You see also the transition from 2dV to 1D near the upstream river. These discretizations lead to a large computing efficiency and enhances numerical stability. Here are the main steps of the barotropic solver. First, a semi-implicit scheme in time is applied to the continuity and momentum equations and the vertical boundary conditions. Divergence and pressure gradient are treated implicitly, which allows to bypass most CFL conditions. The other terms like Coriolis, baroclinicity, horizontal viscosity, and radiation stress are treated explicitly. Then, a Galeckin weighting residual statement, which is a finite element method, is applied to the continuity equation. The momentum equation is vertically integrated and then applied to the bottom boundary layer, which leads to an equation for elevations only. Finally, following finite element procedures, the elevations are determined at all nodes by solving the equation found at step 4. Once the elevations are found, the momentum equation is solved at site centers with a semi-implicit finite element method. The turbulence closure is treated with a finite element method too. The vertical velocity is treated with a finite volume method and prisms like the transport equation. The latter is then solved with upwind or TVD schemes, which won't be detailed in this course. An Euler Lagrangian method is applied to the momentum advection, which is approximated as above. X is a known point, and the objective is to find the location of the foot of the characteristic line x star. Indeed, advections are evaluated by following a particle starting at an unknown point at time t, the FOCL, and ends at a pre-given point at time t plus delta t. This is a Lagrangian process, and it's called backtracking. Finally, I will present you the two options for inundation algorithms. The first one is the default option, and that's the one used in OPENCOASTS. At the end of each time step, entities of the grid, which are elements, sites, and nodes, are updated as wet-dry based on the newly computed elevations compared to a threshold depth H0. The second algorithm requires finer resolution. For it, the shoreline position is updated after each of its nodes has been checked for wetting and drying. For example, on the figure, at step n+1, the shoreline has been updated. A is become wet and B is became dry. Thank you for your attention. We'll speak about how to use schism. We'll start by the basics to run a simulation with it. First, the mandatory input files are the following ones: the horizontal unstructured grid, hgrid.gf3, the horizontal unstructured grid similar as sgrid.gf3, but with coordinates in longitude and latitude. This is used for Coriolis and atmospheric forcing, which are usually given in spherical coordinates. The vertical grid, vgrid.in, the parameter input, param.in, the boundary conditions input, bctice.in, and the bottom friction input with one type of coefficient, the manning, the drag, or the rough, which may be constant or variable on the grid. To run a simple test case with schism, you have to generate a hgrid.gf3 with simple boundary conditions, prepare input files, run a test case with ePres equal to 1, that means with one processor, in order to check the grid quality. Once your simple case is working properly, you can try or add other options. As a simple case, you can try a tidal run with a constant Manning's n. To help you, resources are available on www.schism.wiki. You can perform a pre-processing step to check grid and input issues. For this, prepare the mandatory input files, set ePres equal to 1 in param.in, run schism with one processor only, and check the file fort.11 for fatal errors concerning the grid. Rectify grid input issues and repeat until pre-processing is successful. On this slide, the format of .gf3 and .ll file is detailed. First, you have the comments, which are ignored by code, then the number of elements and nodes. Following that, you have the list of nodes with the nodes number, their coordinates and their depths. The column depths can be different variables. For example, in the Manning.gf3, this is the Manning coefficient. Following that, you have the connectivity table with the element number, the element type, and the nodes defining each of them. Finally, you have the list of open and land segments, which are necessary only for hquid.gf3, not for the other .gf3 files. You have the number of open boundary, then the total number of open boundary nodes, following by the number of nodes for the first boundary, and so on. And then the same thing for land boundaries. To add a connectivity table to a build point file, you can use XMGraded5, which is a tool to visualize most schism inputs. Select triangulate build points. To generate boundary conditions, use also XMGraded5 and select read_dm, create open land boundaries. If there is no open land boundaries, create respectively two land open boundaries linked to each other. These following figures show you how to define boundary segments. After selecting Create Open Land Boundaries, choose Define New Open Boundary. Go in counterclockwise direction from the first point of your open boundary segment to the last one. Do the same thing for the land boundary segment with the option Create New Land Boundary Segment. The created open boundaries are displayed in blue, whereas the land boundaries are in green. The islands are automatically generated as land boundaries and are displayed in red. This is an example of the vgrid.in file, which stores the parameters about the vertical coordinate system used. Here it has been chosen an hybrid SD grid with ivcore is equal to 2. Following this number, there are the total number of levels, the Z levels, and the HS depths. The Z levels starting from the bottom to the transition between S and Z levels, and then you will find the S levels with the parameters the HC depths, theta B and theta F, and the Z levels starting from the transition between Z and S and the surface. Most of the time, in OpenCoast, you will use a 2D configuration with 2 levels and 1 layer. This table brings together all the types of boundary conditions available. You can force the open boundaries with elevations, horizontal velocities, salinity, temperature, and traces. The type 1 is time history forcing, uniform along boundary. The second type is to set a constant value at the boundaries. The third type allows to force boundaries with harmonic ties, and the type 4 is for time and space varying values along boundary. There are other types available. Relaxation can be applied to the boundary input values with the parameter ANU.
Now we'll see the format for a BC tide with a harmonic forcing, which will be the most commonly used. The first line corresponds to a comment, it is ignored. The second line corresponds to the number of constituents for the Earth's tidal potential. Here this is 0. And then these are the number of constituents that are applied along the open boundary. And for each constituent, we'll give, for instance, O1, we'll give the angular frequency, the nodal factor, and the Earth equilibrium argument in degrees for each constituent. Then we have the number of open boundary segments, and for each open boundary segment, we have the number of nodes, and then the value 3 stands for harmonic forcing. Then we will have for each constituent the list along the open boundary of the amplitude and phases, once again in degree. The param.in file corresponds to the main input file for the model. It includes tens of options, but I will just explain you what are the most commonly used. For bottom friction, the bfric flag allows to decide which formulation we'll use for bottom friction. -1 corresponds to a Manning formulation, which is the one used in OpenCoast. The time step dt is very important. We will have a slide dedicated on it. You can use a ramp option. In this case, you have to specify the duration of the ramp in days. For the atmospheric forcing, several options are available through the flag NWS. For the global output options, you can specify how many hydrodynamic time steps you want an output. This is the NS pool variable. And with the EHF-skip flag, you can indicate how many hydrodynamic time steps you want a new output file. This is to avoid to have huge output files. You can also specify the minimum water depth for the wetting and drying algorithm. Other parameters, this is more technical, allow to control the balance between numerical diffusion and dispersion. And another one that is very useful is the ICS flag, which indicates if you are using Cartesian or geographic coordinates. All the other options are described in the user manual and also in a param.in.sample in the source code directory.
Option input files can be added for a more elaborate run. The sflux directory for atmospheric forcings is activated with NWS is equal to 2 in the parent.in file. Several ASCII file.th can be added as boundary conditions or atmospheric forcings. It is also possible to get time series of elevations, air pressure, wind, etc. at particular locations. This is done by set iout_stay at 1 in the parent.file and create a station.in file. More optional input files are detailed in Schism manual. One way to add atmospheric forcings is the sflux directory. You can get netcd files from CFSR, GFS forcings, and others. The sflux directory must be created and contains the sflux inputs.txt, which groups info about the forcings and various netcd files depending on the forcings you applied. Sflux air for wind speed at 10 meters above mean sea level, air pressure, surface air, temperature, and specific humidity. Sflux rad for wave radiation fluxes and sflux PRC for surface precipitation rate. The latter two files are used respectively in heat exchange and salt exchange only. The format of the sflux air file is specified in the sflux_90 file. Regardless the complexity of your run, you have to pay attention to the CFL number. It corresponds to the sum of the flow velocity and the surface wave celerity multiplied by the ratio between the time step and delta x. As Schism is an implicit model, it needs CFL greater than 0.4. If this rule is not applied when the grid is generated, the results can be affected by numerical diffusion from the ELM method. The figure shows the operational range for time step with a given grid size. When the time step is too small, diffusion error can occur. When the time step is too large, truncation error can occur. These are the recommended ranges for both barotropic and baroclinic modes. For barotropic applications, you can set delta T between 100 and 400 seconds. For baroclinic applications, you can set it between 100 and 200 seconds. However, for very detailed application or for laboratory test case, you can go down delta T to 10 seconds or less. Define the smallest time step you consider for the application and use the condition CFL greater than 0.4 to calculate the course's grid size at each step. If you reduce delta T, you may have to refine the grid. If you coarsen the grid, you have to recheck the condition. If you refine the grid, you do not need to reduce delta T, which shows the efficiency of Schism as an implicit model. Now we'll see how the outputs are treated. You can find info about the progress of the run in the mirror.out file. Most of Schism outputs are generated in the outputs directory, which has to be created before the run. The global outputs are distinguished by their name, which contains the processor number and the stack number, which stores a certain number of outputs defined by the user at the beginning of the run. When the station.in file is configured, you obtain station outputs called stout 1, 2, 3, etc. Each contains one variable for all the stations defined. At the end of the run, it's necessary to combine the outputs provided by each processor before analyzing them. You will find scripts to do it in the utility directory. Then you have several ways to visualize the outputs. Some tools are available like XMV6 and Visit, or you can create your own tools with Python or MATLAB, for example. You can extract time series with the station outputs or with Fortran scripts. Other scripts for performing harmonic analysis or computing residuals are available. We'll give you now some recommendations of 2D or 3D model runs to check your results. When you're running a 2D model, examine surface velocity in animation mode to find potential issues. Be careful to define negative river flow values for inflow. When you're running a 3D model, add some other tasks. Use the one-way nesting capability to generate velocity boundary condition at the open boundary. Avoid large bottom friction in shallow areas in 3D regions. And control the balance between numerical diffusion and dispersion.
This diagram shows the whole range of possibilities of schism as a modeling system. So you can see, starting from the upper part of the diagram, we can simulate sediment transport, generic tracer, turbulence, data assimilation, particle tracking, and with some applications for all spills, you can compute the age of the water. We have some sea ice options under development, an oil spill model, ecology biology, water quality, and also short waves, which is now coupled with a tidal march model.
Finally, this is an overview of the domain decomposition. The domain is divided into non-overlapping subdomains element-wise, not necessarily contiguous. Each of them is taken by a processor. To allow the exchange of info between each subdomain, they are augmented with one layer of ghost elements. Thank you for your attention.
Hello everyone, I'm Laura Labo. I'm a PhD student in La Rochelle University in France, and I work with Xavier Bertin. If you have any question of this course, please, I can answer to it. Okay. Does anybody have a question, or we can go to the next course?
Good morning, everyone. I'm Alberto Azevedo from UNEC's team, and for now we're going to take a short break of 15 minutes. We should return at 11:35 or 10:35 for the Portuguese team. So 15 minutes. Thank you.
Hello, everyone. Welcome back. We are going to continue with the next lecture.
Good morning, everyone. My name is Xavier Bertin. I am a researcher at the Joint Research Unit Liens in La Rochelle University, and today I will tell you about the wind wave model and its coupling with schism in the framework of OPENCOASTS. Here is the outline of my presentation. I will start by a general introduction. I will present the physical formulation of the wind wave model. I will follow on with the numerical methods used in wind wave model. And finally, I will explain the coupling between wind wave model and schism. Chapter 1. General introduction. Shortwaves have many environmental and socio-economic impacts. They control the hydro-sedimentary dynamics of coastal zones, particularly during storms. They contribute to storm surges and extreme water levels. They resuspend bottom sediments and control water turbidity. They mix the ocean upper layers. They impact heat and momentum fluxes with the atmosphere. They can damage vessels and coastal structures, and many more. Therefore, the numerical modeling of short waves is of fundamental importance. Wave models can be categorized in two main families. The first family is a family of phase-resolving models, like Boussinesq or Serre-Grignagli models, like fan waves or bows, shallow water models with a pressure correction terms, like SWASH or the non-hydrostatic version of X-Beach. On the right-hand side, you can see a movie of the shortwave propagation computed with SWASH at a beach located in the southwest of France. Last one are CFD and RANS model like NH wave and EH wave. However, representing shortwave individually require a very small spacing, typically less than 1 meter, and very small time step. So these models are very time consuming and can hardly be applied at scale, let's say larger than 1 kilometer. Second family concerns phase average models or spectral models like SWAN, WaveWatch3, WAM, or the wind wave model. In these models, the short waves are not represented individually, but the mean energy associated with the short waves is computed, their generation, their propagation, and their dissipation. Chapter 2. Physical formulation of the wind wave model. Spectral wave models solve the wave action equation introduced by Coman and Tal. In this equation, the first term corresponds to a change in time. The second and third term correspond to the advection in geographic space. The fourth term corresponds to the advection in frequency space, and the fifth term corresponds to the advection in directional space. On the right-hand side, S corresponds to the sum of the source term. The variable that is solved is the wave action, and the wave action corresponds to the discrete wave energy divided by the relative frequency. This quantity is preferred to the discrete wave energy because it is conserved in the presence of ambient currents. The source term corresponds to the dissipation by breaking, dissipation by bottom friction, the growth due to the wind, and the dissipation by whitecapping. On the right-hand side, you can see a figure corresponding to a directional wave spectra computed by the operational wave model of Ifremer in France. First process represented in the wind wave model is the dissipation by depth-limited breaking. One of the most widely used models is the one introduced by Batches and Janssen. In this model, alpha is a parameter that corresponds to the dissipation rate, basically the type of breaker, spinning breaker, plunging breaker. This is a tunable parameter. FM01 is the mean frequency. QB is a fraction of breaking waves. D is the total water depth. Gamma is a breaking index that corresponds to the maximum wave height for given water depth. Again, this is an adjustable parameter. And E tot is the total wave energy. Just to illustrate the impact of this gamma parameter, I will show you an application of the wind wave model to the southwest of La Rochelle. On the Oléron Island, this is a dissipative beach, very flat beach. The upper panel corresponds to the topography of the beach, and the black circle corresponds to the location of the sensors where we measured wave height. So the orange curve corresponds to the model with the default breaking parameter, 0.73, while the blue one corresponds to gamma adjusted to 0.5, and you can see that the observations are much better reproduced with the root mean square error divided by a factor of 3. And this parameter can be adjusted in OPENCOASTS. Second process is the dissipation by bottom friction. One of the most widely used models to represent bottom friction in spectral models was introduced after the John Swap project. In this model, Gamma is a tunable friction coefficient that depends mostly on the bottom nature. F is the wave frequency, E is the discrete wave energy, and D is the total water depth. To give an idea of the impact of this friction coefficient, I will show you another application of the wind wave model on the Oléron Island as before, but this time on a rocky bottom, a rocky shore. And as you can see, the blue model with default parameter for the bottom friction corresponding to sand substantially overestimates the wave height by almost half a meter. And if we adjust the friction coefficient to a value corresponding to a rocky bottom, then we are able to eliminate mostly this bias and divide the root mean square error by a factor of 2. Chapter 3, numerical methods used in the wind wave model. As we have seen before, spectral wave models solve the wave action equation. The wind wave model solves this equation on unstructured grids. The wave action equation is solved using a fractional three-step method, as in WaveWatch 3 or 1. First, the advection in geographic space is solved using the explicit end scheme introduced by Abgral. Second, advection in spectral space is solved using the finite difference method ultimate quickest proposed by Leonard. Finally, the source terms are integrated using a Runge-Kutta TVD approach. However, the explicit scheme for the advection part implies respecting the following CFL condition, where Cg is the group speed, U is the mean current velocity, dt is the time step, and delta x is the mesh size, and this quantity should be lower than 1. In this example, the mesh size goes down to about 10 meters in a water depth of 10 meters, which implies that the time step should be of the order of 1 or 2 seconds, which is very small. In wind wave model, sub-iterations are performed to satisfy this condition, but so-called splitting error can occur if delta t is too large. To explain this problem, if the time step is too large, the waves will travel over a large distance within a time step, while the source terms are integrated locally, which will create some kind of inconsistency. To overcome this issue, fully implicit schemes are used in OPENCOAST. Last section, the coupling between the wind wave model and schism in the framework of OPENCOAST. Both models are coupled at the source code level, which means that there is no coupler, and directly share variables through memory. The wind wave model will provide schism with fields of radiation stress, we'll see in the next slide, friction velocity, for instance, while schism will provide the wind wave model with fields of surface elevation and velocity along x and y. Both models share the same unstructured grid and the same domain decomposition, which means that there is no interpolation and the coupling is very efficient. In this figure, you can see one of the largest applications that we did in La Rochelle. This is a grid that covers the whole Northeast Atlantic Ocean with a resolution that ranges from a few kilometers in deep water to 3 meters along the shoreline, along the dikes and the barrier that prevent usually from flooding. First, the effect of short waves on the mean circulation. In the near shore, when short waves dissipate, their momentum flux decreases, which acts as a horizontal pressure force, which will drive currents as well as a wave setup along the coast. In OPENCOAST, this effect is accounted for using the radiation stress formalism introduced by Longet-Higgins and Stewart in the momentum equation. So these are these additional terms in blue, where SXX, SXY, and SYY correspond to this radiation stress, and tau S and tau B are the surface and bottom stresses that can also be wave dependent in the code, but not in OPENCOAST so far. To give you an idea of the importance of this process, I will present you briefly an application that we did in the southern part of the Bay of Biscay during Storm Klaus, where we investigated the contribution of shortwave braking to storm surges. These storm clouds produce the largest waves that were recorded close to the coast over the last 2 decades, about 13 meters significant wave height, a few tens of kilometers from the coast. So this was a storm particularly indicated to investigate the impact of these big waves on storm surges. So in black, this is the observed storm surge at 2 stations, Arcachon in the upper panel and Bayonne in the lower panel. And what you can see is that only the fully coupled model that accounts for the radiation stress is able to capture very accurately the peak of the storm at this both station. If we do not consider this effect, this is a red curve, we miss the surge peak by almost half a meter. And the error is increased by a factor of 4. The other way around, the mean currents will also impact the wave field. This is represented in the wave action equation with the term U and V in the advection part. To illustrate the importance of this process, I will present you briefly a study that we carried out at the mouth of the Tagus estuary near Lisbon in Portugal, where we made a large field experiment that we complemented with an application of the wind wave model. And what you can see is that at mid-flood, the waves along the coast, they are much bigger compared to mid-ebb. There is a factor of 3 between both. What is happening is that the flood currents, they enhance wave refraction so that the waves better reach this stretch of the coast. And this process is very well reproduced by the model and matches well the observations. When the currents get stronger, they will cause a shoaling and a steepening of the short waves. And if the currents are really strong and the water depth is small, then the waves will be so steep that they will start to break due to white capping and they will dissipate. To illustrate this process, I will show you another application to the south of the Oléron Island in France, where we carried out a large field experiment. And I just show you time series of wave height and water depth upper panel, wave height lower panel. In black, these are the observations, and in blue, these are the results of the wind wave model. And as you can see, if you look carefully, for a given wave height, these are the black dotted line, the wave height is 2 times larger at mid-flood compared to mid-ebb. This is really a process of dissipation. The higher part of the wave frequency spectrum will dissipate because the waves are so steep that they will start to break. And this process, again, is well represented and reproduced in the wind wave model. Thank you for your attention. Should you have any question, please just go ahead. And if these questions come later, please contact me by email.
Okay, once again, it's Laura Lavo. Do you have any question on this course?
Roger Proctor here. Just in the last talk, then the example of improving the storm surge by including the waves. How good do the waves come out under those circumstances?
What? Can you repeat, please?
Okay. Yeah. So the example showed that the including the wave field improved the storm surge.
Yeah.
Yeah. I was wondering how good was the performance of the waves?
You mean the representation of the waves in WWM?
Yeah. We saw comparisons with sea level, but we didn't see a comparison with wave height at the coast.
You have you speak about, for example, root mean square error, about percentages?
Ah, just a picture would be good.
Okay. Wait a minute. I have pictures with significant wave height and mean period at different wave buoys.
Yeah, that'd be good.
Okay, I will share. Okay, this is from Lavo et al. And you can see the different the significant wave height and mean period at different locations. So, and you have the root mean square error on it, and the normalized one, and you are about between 10 and 20% of error.
Yeah. Okay. That's just interested to see how the different components of the model actually interact. Yeah, and we just saw one of them, so it'd be nice. It was nice to see the other one. Thank you.
You have the localization. Oh, can catch it. Yeah. So you have the different buoy with the blue triangles. So the Biscay buoy, Bilbao, and Capri, and it corresponds to the picture that I just showed you here. No, so it's the atmospheric forcings here. So
Thanks, Laura.
is there any more questions about this course? Okay, if you have another question, if somebody has another question, you can ask in the chat. Okay, so maybe we can go to the next course. Yes, no problem for the link.
My name is André Fortunato, and I would like to welcome you to this tutorial on the generation of triangular grids for coastal and ocean models. This tutorial is split into two parts. This first part of the tutorial will cover some basic concepts and theory behind finite element grid generation. Then in the second part of the tutorial, I'll show you how to generate a grid using specific software. By the end of the tutorial, I expect you to be able to generate a finite element grid using a grid generator. So in the first part of this tutorial, I will explain what a finite element grid is, and I will show you some software available for grid generation. Then I'll show you in detail what are the major steps in grid generation. So what is a finite element grid? Coastal processes are described by partial differential equations. These partial differential equations express physical laws like the conservation of mass, of momentum, or energy. In general, these equations do not have an analytical solution, so they have to be discretized and then solved numerically. A finite element grid is simply an approach to discretize a continuous domain. A finite element discretization offers a piecewise continuous description of the variables with varying resolution. Nodes and elements of the grid will determine where the equations are solved and how the spatial gradients are evaluated. What kind of information do we need in a finite element grid? A finite element grid includes the location of the nodes, the depth at the nodes, the definition of the elements, which is simply an ordered list of nodes that define each element, and the definition of the boundaries. Together, the location of the nodes and the depth of the nodes constitutes what is called the table of nodes. Also, the definition of the elements is often referred to as a table of elements. So here's an example of a finite element grid, in this case for the Tagus estuary here in Portugal. You see that this grid is formed by triangles. The nodes are the vertices of the triangles. The elements are the triangles themselves. The depths here are shown as colored contours. And finally, the boundaries are represented by the thick lines. Now, as you can imagine, generating a grid like this one can be extremely time-consuming. Software for grid generation has therefore been developed over the years to simplify this task. Grid generators are codes that help us build grids efficiently and with good quality. There are many grid generators out there, and this is just a partial list. Some of these codes perform all the tasks required to generate grids, others only perform parts of them. Some were specifically designed for coastal modeling, others are more generic. Each of these codes has its own advantages and disadvantages, and it's up to you to choose the grid generator that best matches your needs and skills. Now, even though all these grid generators are different, and each grid generator has its own procedure or procedures to generate a grid, there are some common tasks in this procedure. So, in the following slides, I will show you what these common tasks are so that you get acquainted on how to generate a grid. So let's suppose this figure represents an estuary, the estuary that you want to simulate. Your first task will be to define the domain that you want to simulate. Once you have defined your domain, you need to place the nodes that will constitute your grid. Remember that this is an unstructured grid, so the node placement and the node density can vary widely in space. You can have very fine grid resolution in some areas and very coarse grid resolution in other areas. Once you have the nodes, you have to define the elements. So for a given set of nodes, you can have different sets of elements or slightly different sets of elements. Once you define the elements, you have a preliminary grid, but you may not be fully happy with that grid. So at this point, you'll want to optimize and verify your grid and check that your criteria are obeyed. For instance, this can involve adding more nodes or moving nodes around or adding more elements. Once you are satisfied, you can then interpolate the bathymetry on your grid and then define your boundaries, namely specifying where are the open boundaries and which boundaries are closed. So in the next few slides, I'm going to go over these several steps and explain how you go about doing each of these tasks. Let's start with the domain definition. If you are modeling an estuary, you have to define where your upstream boundaries are located and where your downstream boundaries are located. Starting with the upstream boundary, you'll want to extend your model domain beyond tidal intrusion. If you are modeling salinity, then you want to make sure that your upstream boundary goes beyond the salinity intrusion limit. This will simplify the way you impose your boundary conditions. But even if you only have a barotropic model where you are only simulating tides, you'd like to have your upstream boundary further away than the limit of tidal propagation. However, in many cases, you are limited by the availability of bathymetric data. Very often we have bathymetric data in the estuary, but we don't have data in the river. Now, downstream, you want to extend your domain as much as possible to deep waters where velocities are small. This will minimize the possibility of numerical problems at the boundaries. So in general, you don't want to place your boundaries in areas with strong velocities. In particular, you don't want to place your boundaries in areas that are affected by the tidal jet. Also, you'd like to make your boundary geometrically simple as possible. So in general, your boundaries will either be a straight line or a curvilinear line. So here's an example of how we specified the boundaries and how we defined the domain for a specific case. So we are modeling the Leixões Harbor in the north of Portugal. That's what you are seeing here in this figure. So right here you have the first choice that you have to make. there's a river flowing into this harbor, and we have to specify the limit of the river somewhere. At this point, we specified the boundary, considering that we didn't have any bathymetric data in the river. So we forced the boundary to be the limit of the harbor. This was also made possible by the fact that this is a very small river, and so the river flow doesn't have a significant effect on what's going on inside the harbor. Now, if we zoom out, you see that we included an estuary, the Douro estuary, in our domain. So here we have a second river boundary, the river boundary of the Douro River. In this case, it was very simple because there is a dam that limits tidal propagation. So our upstream boundary in the Douro is determined by the existence of this dam. If you zoom further out, you can see the full extent of our model domain. Here you see that our model domain is much larger than the area that we want to simulate. And the major reason for that was that there is a wave buoy in this area that you can see on the figure. And we defined the domain such that we had the wave buoy inside the domain, and we could use it to validate the wave model. So the second step in our series of tasks to generate a grid is to place the nodes. There are a bunch of different criteria that are used to decide what is the density of the nodes that we want to use in each part of the domain. Probably the oldest criterion is called the minimum dimensionless wavelength criterion. Suppose you are modeling a wave and that you decide to use 10 nodes per wavelength. So suppose you are modeling the propagation of a wave and that you have about 10 nodes per wavelength. That's what you see here, this L over delta x equals to 10. This is how the model sees your wave. Your sinusoidal wave is clearly not properly reproduced. If instead of 10 nodes per wavelength, we have 20 nodes per wavelength, then you see that the wave is much better represented. But still, you can see some angles in the curve that you're seeing in front of you. If we move to a grid with 40 nodes per wavelength, now you see that the sinusoidal wave is much better represented. And for instance, if you compare it with a grid with 60 nodes per wavelength, there are very few differences. So overall, we consider that a wavelength is properly represented if we have 40 to 60 nodes per wavelength. Now, as I said, this was an old criteria that was used very often in the past. However, nowadays grids are very fine and this criteria is not very useful. The exception is when we are simulating waves that have very small wavelengths, like tsunami waves or even infragravity waves. A second criterion is the need to resolve a channel. Suppose this is a cross-section of a tidal channel where you can see the bottom and the free surface. Suppose that you are representing this geometry with 5 nodes, as you can see here. Then here's what your model will see. This is the cross-section as seen by our model. Clearly, there are huge errors in the representation of the cross-section, and therefore this grid is not fine enough. So it's important in your model to properly represent the cross-section of the channels, and the exact number of nodes that you need will depend a lot on the complexity of that cross-section. So I wrote here 4 to 6 nodes, but of course it may be more if the cross-section is complex, as it was in the figure that I just showed you. A third criteria that you have to take into account is the representation of sharp bathymetric gradients. For instance, when you're modeling the propagation of a tide over a shelf break in the continental shelf. This figure was taken from a paper from Scott Hagen and co-authors, and you can see here a cross-section of the topography with the deep ocean, the continental shelf, and a shelf slope. Now, these authors simulated the tidal propagation over this domain using a uniform grid. Then they computed the truncation errors using this grid. Here are the errors that they found, and it's clear that there are sharp peaks of errors, sharp, very strong errors, wherever the shelf, the bottom slope changes. So it's clear that in areas where you have a strong change in bathymetric slope, you'll need a finer grid resolution. A fourth issue that you have to take into account is the need to resolve the solid boundaries. This is especially important inside estuaries. Let me give you an example. This is a piece of the Tagus grid that I just showed you a while ago. This is a piece of grid of the Tagus estuary that I showed you a few slides back. These strange colors that you see here are due to the presence of a marina, the Cascais marina, that is not represented by the grid. The reason I did not include the Cascais marina in the grid originally was because the area of interest inside the Tagus estuary was very far from this area. Still, it's clear that we won't be able to represent properly the flow inside the marina and around the marina the way we are representing it with this grid. Now, if you try to represent the marina with the grid, you see that the extra effort represented by the additional nodes that I am including in the new grid is very small. So with very little effort, I can represent the marina, and therefore I can better represent the flow in this area. A fifth issue that you have to take into account in the node placement is the sharp velocity gradients. For instance, if you have an ebb jet from a tidal inlet, you'll have strong vortices, strong velocity gradients, and you need a fine grid to represent those. Besides the density of the nodes, you'll also want to take into account that the grid resolution should vary smoothly in space. This promotes both accuracy and stability. You have better accuracy because you minimize the truncation errors, and you have better stability. This will depend on the models, but in general, you'll tend to have more numerical errors and numerical oscillations if your grid resolution varies very rapidly. Now, once you have your nodes defined, it's time to define your elements. Most grid generators use the so-called Delaunay triangulation. The Delaunay triangle has a very simple property. If you have any four nodes that will give you two different elements, no circumcircle of any triangle will contain any of the other nodes. So this figure shows you an example of triangles that do not meet the Delaunay criterion. But if you swap the central edge and make two different triangles with the same nodes, then these triangles will meet the Delaunay criterion. You see the two circumcircles of the two triangles, and you see that neither of them contains the fourth node. Now, once you finish doing your triangulation, you have a grid, and now it's time to optimize it to verify that it meets your standards and improve that grid. In general, the goals are to reduce the skewness, so to avoid having triangles that are very skinny. You want to minimize the maximum number of neighbors per node, so the number of nodes that are connected to any node. You want to make sure that you have a smooth transition between element sizes. And in some cases, for some models, you want to prevent angles, internal angles of the triangles above 90 degrees. The typical operations to improve the quality of the grids are to add nodes, to delete nodes, to move nodes, and to swap the edges of the triangles. So here are a few examples of different grids that you can slightly change to turn them into the grid that you find in the center. For instance, if you look at the three grids on top, there is one node that can be eliminated without, in order to provide a better grid. If you look at the two grids in the bottom on the left and on the right, you see two element edges that can be swapped in order to obtain a better grid. So here's a more detailed example of how we can optimize and improve a grid. This figure shows a piece of a grid in the Atlantic. and you see these circles represent elements that are not terrific. This was a grid generated with XMGR-edit, and here's how we can improve it. In general, you see that we avoided nodes that were connected to 8 other nodes. So in this case, the maximum number of neighbors is 7 rather than 8. We also avoided nodes that were connected to only 4 other nodes. So now the minimum number of neighbors is 5. So there are a bunch of operations that can be done, and I'll go into more detail in the second part of the tutorial. So these were the major steps required to generate a finite element grid. In the second part of this tutorial, we will see how these concepts can be applied in practice to generate a grid. Hello again, and welcome back to my tutorial on finite element grid generation for coastal and ocean models. In the first part of the tutorial, I covered some basic concepts and theory behind finite element grid generation. In the second part, I'll show you how you can generate a grid using specific software. To generate this grid, I'll be mostly using a code XMGR-edit. So I'll start by introducing you to this code. Then I'll show you how you can use GR-edit together with another code called NiceGrid to quickly generate an acceptable grid. So what is XMGR-edit? XMGR-edit was developed by Paul Turner and Antonio Batista at the Center for Coastal Land Margin Research and more recently at the Oregon Health and Sciences University. GR-edit is a Unix Linux-based code, so you'll find it easier to use if you have at least some familiarity with these operating systems. GR-edit was developed specifically for coastal modeling, so it has a lot of features that are particularly useful for to generate this kind of grids. GR-edit is a semi-automatic grid generator. This means that it does have a lot of capabilities to edit the grid in detail, but it also has some capabilities to generate the grid automatically. GR-edit offers a lot of features like node placement, triangulation, quality control and grid editing, definition of the boundaries, and interpolation of the bathymetries. So you can do everything you need to do in a grid using XMGR-edit. How do you launch XMGR-edit? If you already have a grid, you simply type XMGR-edit 5 and then the name of your grid. Of course, when you get started, you normally don't have a grid yet. In that case, you may have, or you should have at least, the bathymetric points that you're going to use to generate your bathymetry. In that case, you can launch GR-edit using this command here, XMGR-edit 5 -b, then the name of your points file -w, and GR-edit will read these points and generate a grid based on those points. Finally, if you don't have any information at all, you can still launch GR-edit as follows: XMGR-edit -W 0011. If you do that, GR-edit will build the simplest possible grid, which contains the points 0, 0, and 1, 1 as nodes. So you get this simple grid with only 2 triangles. Of course, this grid is not very useful, but this can be a useful way to start getting to know XMGR-edit and trying it out. Now, when you normally launch GR-edit, this is what you see. You see your grid in the middle of the screen, and then you have 2 different menus. You have a menu on the left that defines what you see. So this menu helps you zoom and pan, and you can toggle on and off the elements that you want to see displayed. Then you have a second set of menus on the top of the window, where you can read and write files, change the display, locate nodes and elements, edit nodes and elements, define regions, compute boundaries, and so on. In this short tutorial, I won't have the time to go over all these menus, so you'll have to rely on the user's manual for this. However, as we go along this tutorial, each time I'll do an operation with GR-edit, I'll show the respective menu in blue. So whatever letters you'll find in blue means that I'm talking about the menu, and normally the top menu. Now, GR-edit has 3 major building blocks. The first is what we call the background grid. The background grid is a grid that cannot be edited, and normally it contains the bathymetry, and that's why it cannot be edited. So this will not be the grid that you'll be generating. It is represented in orange, as you can see on the screen, and you can toggle it on and off at on the left on the menu that says background grid. So you can see the grid, its bathymetry, and its boundary if you have read one. The second building block of GREdit is the edit grid itself. So it's the grid that you want to generate. This grid is changeable, so you can edit it, you can add nodes, remove nodes, delete elements and add new elements and so on. It is represented in black, and you toggle it on and off again on the left on the edit grid menu. So you can see in this case not only the grid, the bathymetry and the boundary, but also the nodes and the node numbers, the elements and the element numbers, and the depths of the nodes. The third and last building block are the build points. The build points can be created, moved, killed, and so on. They're normally used when you start generating a grid. You start by putting the build points, and then you transform those build points into nodes of a grid. They're always represented as black squares, and you can toggle them on and off at the build point menu on the left. So in a nutshell, this is what GREdit looks like. So in the next few slides, I'm going to use GREdit to generate a grid. At this point, you must realize that generating a grid can be extremely time-consuming. How long it takes you to generate a grid will depend on a lot of things. It depends on how large and how complex your coastal system is. It depends on how picky you are with your grid. It depends on how sensitive your model is to the quality of your grid. It depends on the quality of your grid generator, of course, and it certainly depends a lot on your skill and experience with a grid generating tool. For the purpose of this presentation, I selected a very simple estuary, a very small one. It's probably the smallest estuary I ever worked with. It's the Ave estuary in the north of Portugal that you can see in this picture. So generating this grid will probably be a bit simpler than usual, but the type of operations that you do is the same even for a much larger estuary. So what do you need to get started? First, you need the background grid, you need the bathymetry. This is what you see here in orange. So this bathymetry is composed of two different sets of information. We have a very detailed bathymetric survey in the estuary, and then we have a much coarser resolution bathymetry in the coastal area. The second thing that you need is the definition of your domain, where your grid will be located. That's what I'm calling here the coastal boundary. This coastal boundary was generated in two steps. In the coast, I simply digitized a nautical chart to obtain the line that you see on the right. Then in the ocean, I used GREdit itself to generate a circular part of the grid, and then I joined the two pieces together. Of course, you can do this with other software like ArcGIS, for instance. There are certainly many ways to generate this boundary. So now we must look at our domain, and we must realize the following. We have a very small estuary. Inside this estuary, we want to have a very fine grid resolution. The estuary is narrow. We have a lot of detail that we want to represent, and therefore we need a very high density of nodes. Then as we moved away from the estuary, the grid can become progressively coarser. And it can be progressively coarser because the depth increases and the velocities decrease. So the first thing I'm going to start to do is generate a bunch of build points that you see here in order to define a spatially varying grid spacing. I do this by first generating these concentric build points using build circular spread, and then I put the other points by hand using place build points. Now once I have those points, I can triangulate them using triangulate build points, and I get an auxiliary grid. Note that this grid is by no means the grid that you want to generate. It's simply an auxiliary grid that we're going to use to define the grid spacing that we want. So to define this grid spacing, I simply go to regions, create region, and I create a region that includes all the points in the outer circle. Then I go to edit, edit over grids, regions, evaluate, and then I define the depth as the grid spacing that I want in this area. So in this outer area, I'm specifying a grid spacing of 1,000 meters. As I said before, we want a finer grid resolution in the estuary and then progressively coarser as we move towards the edges, the outer edges of the domain. So I specified 1,000 meters in the oceanmost region, then 500 meters, 250, and then 10 meters inside the estuary. So when you do this, you get this grid with this bathymetry, where the bathymetry represents the grid spacing that I want, which goes from 10 meters to about 1,000 meters. At this point, you may want to save your work so that you don't lose it later. So here comes the really tricky part about this approach. As I said, GREdit is a fairly old code. It was actually developed about almost 30 years ago, even though it was improved over the years. And the approach that it has to automatically place the build points is based on the dimensionless wavelength criterion that I told you about in the first part of this tutorial. However, we don't want to use this criterion. Instead, we want to use the grid spacing that we just defined. So we're going to trick GREdit into doing what we want, into placing the build points with the grid resolution that we want, but thinking that is using the dimensionless wavelength criterion. To do that, we're going to generate a fake bathymetry to get the grid spacing that we want. So we set depth equals to 1 over g times alpha s over t square. So here g is gravity, s is the desired grid spacing that we just defined, alpha is a dimensionless wavelength, and t is a wave period. I'll come back to this alpha and t later on. So to do this, we simply go to edit, edit over grids, regions, evaluate, and then we impose the equation that I just showed in the previous slide. So here we are using alpha equals 25, so alpha is a dimensionless wavelength criterion, and t equals to 14,000 seconds. Notice that these values are not mandatory. These are free parameters, and you can use other values provided that you are consistent later on, and we'll come back to this. Again, you may want to save your work, so you can again go to File, Save, and save this new grid aux.grd as an edit grid. So now we have everything that we need to generate the build points. So what we're going to do is to load the auxiliary grid as a background grid, so the grid that we just saved, and then load the coastal boundary as an edit boundary. And you'll see what you have on the screen. So now we have the domain that we want, where we want to generate our grid, and we have an auxiliary grid which helps us define the grid spacing that we want. So at this point, you can start generating your points automatically by going to Build Automatic Placement. You'll get the pop-up that you see here on the screen, where you have to define the minimum dimensionless wavelength and the shortest wave. Now it's here that you must be consistent and use the same values of alpha and t that you used previously. So 25 for the minimum dimensionless wavelength and 4.1 hours or 14,000 seconds for the wave period. So when you hit accept, GREdit is going to generate the build points for you automatically. This may take a while depending on how big your grid is, but this is done automatically by GREdit. So here we have a set of build points created automatically that obey the desired grid spacing. So at this point, you're going to take these build points, triangulate them, and obtain a first cut of your edit grid. So you go to Build, Triangulate, and GeoEdit creates this grid for you using the build points as stepping stones to get your grid. So you see that although we do now have an edit grid, the quality of the grid is awful. You see that we have a lot of very skinny elements, and most models will have a major problem running with such a lousy grid. So we'll have to improve this grid, and we'll come back to that later. The grid is relatively small. It has about 16,000 nodes, which is much smaller than usual, but that's because, yes, this estuary is very small as well. So we have to improve this grid, but before that, we can now define the open and land boundaries. You do that in GeoEdit by going to Boundaries, Compute Boundary, and then grid them, create open land boundaries, and specifying what are your open boundaries and what are your land boundaries. At this point, you have to save your grid, save your boundary file, concatenate them both into a new grid file, and that's the one you're going to work with. So, as I said, we now need to optimize the node placement and to optimize the grid. You can, of course, do that with XM GeoEdit. It's perfectly doable. However, it is very time-consuming, especially if your grid is much larger than the one that I have. Instead, you can use another code called NiceGrid. It's a command line code that was developed specifically to optimize grid. The format is simply to type NiceGrid2 in the name of your input grid file, the name of your output grid file, and then a parameter which is 2, which is related to the way it's going to treat the boundaries. So what does NiceGrid do for you? So here's the grid that you generated with XM GeoEdit. Again, with the right grid spacing, but with a lot of quality issues. And if you run it a few times through NiceGrid, you obtain the second grid that you see here on the right. You see that the grid resolution is very similar. Actually, the number of nodes of the two grids is very similar, but we got rid of all these nasty problems of very skinny elements that we had along the boundaries. There were a lot of improvements in this grid, and they were done totally automatically, so it didn't have to interact with the grid. Now, this second grid is a very decent grid, at least at this scale. If you zoom in, you may see some small problems that remain and that probably will have to be improved using GeoEdit. But to get started, you already have a very decent grid. So we're getting there. The last thing that you need to do is to interpolate the bathymetry, which you do by loading the bathymetry in the background grid, and then interpolating the bathymetry using grid-dem load bathymetry. And that's it. You have the grid that you need to run your model. So you can get these codes, all of these codes, through the Schism platform. You can download Schism that includes XM GeoEdit as one of the programs included. You can load the XM GeoEdit's user's manual, and you can get the NiceGrid code, which is a Fortran code which you will have to compile. So now you know how to generate a finite element grid. Go ahead, give it a try. Thank you for your attention.
Hello everyone, this is André Fortunato. So if you have any questions on grid generation, please feel free to ask them. There was already a lot of discussion on the chat, but if you have other questions, please go ahead now.
André, good morning. Can you hear me?
Yes, yes, go ahead.
I was wondering about the XM GeoEdit is to do a 2D grid. That's all right? What I'm thinking?
Yes.
How can I use that to do the vertical grid, or I cannot do it and have to use the SCHISM. SCHISM.
Schism?
Schism. I don't know.
ISM is the numerical model, and XMGRedit is the grid generator.
Yeah.
So use XMGRedit to get the grid, to develop a grid, and then you're going to use it to run Schism.
Okay.
You'll need both.
Okay, but what I'm asking is, how can I do the vertical grid to run like the different types of vertical grid that we saw earlier by Madame Laval?
I'm sorry, there is a lot of background noise, and I really have a problem understanding.
So it's easier now. I'm putting the mic in front of my mouth now. What I'm asking, how can we do the vertical grid? Because we only saw the horizontal one, the vertical, like taking into account the boundary, the boundary and the bottom of the ocean. That's why I'm asking, because when I'm running some numerical models, I have to do this difference between the vertical grid.
I'm sorry, I'm really having trouble understanding what you are saying because the sound is lousy.
André, this is Marta Rodrigues. André, I think the question, but I'm not sure, I also had trouble, but I think the question was how to view or how to build the vertical grid. But
oh, okay. So the vertical grid is not built with XMGRedit, okay? So if you are running the model in 2D, you will not have to generate a vertical grid. OpenCoast will do it for you. If you want to run the model in 3D, then you have to generate a 3D grid. But that 3D grid is relatively simple because it's really a 1D grid in the vertical, and you generate it with a grid with a word processor. So you generate it by hand. So it's not something that you'll need specific software to generate the vertical part of the grid. I'm not sure I answered your question. That's the way.
Yeah, you answered my question.
Marta was trying to translate for me.
Thank you, Marta, and thank you, sir, for your kindness. Have a nice day.
Thank you. Trick Teixeira trying to speak, but you are mute.
Can you hear me now?
Yes.
I have a small question about the grid generation. Thanks for the talk. When you have flooding, wet and drying, what is the criteria you use to establish the boundary on your grid?
Well, you mean how far inland do I go?
Yeah, you should, because you have to decide where to put the boundary. Mm-hmm. So what is the criteria you use?
Well, normally I tend to have some idea on how high the water can go.
Okay.
From using field data. So that's where I start. So I look at I think that the inundation will go up to, say, 5 meters.
Okay, so is the same criteria I use. So if it reaches the boundary, means that you need another grid. Yeah, because it's not enough to accommodate the wetting on that area. So that's okay. It was just to change some ideas about the process. Usually I use, so you have initial guess for how far the flooding will go. Yeah, exactly. So that's it. Okay, thanks a lot.
I see some questions here in the chat. Is it possible to generate a grid in EOSC-hub and then put it on Delft 3D? Really, I never use Delft 3D, so I don't know what the exact format of Delft 3D grids is. It's likely that the format's not exactly the same, but it's probably you can use the same XMGRedit, and then maybe you'll need to change the format of the input files because it's probably different. For instance, some of the software that I mentioned in the first tutorial use different grid formats. For instance, GMesh uses a different grid format, but the information is the same, so you just need to change the format.
Andre, can I ask another question?
Yeah.
Andre, can I ask another question?
Yes, please go ahead.
So typically this editor you were showing us is of the type nodes first. Is that true? And so you have to put
Yes.
the nodes first on your domain, and after you use Delaunay triangulation to join them on the first cut, say.
Exactly.
Is that true? Okay.
Yes. Okay, there is another question here saying, is Nice Grid also handling mixed quad-tree element grids? Well, the version, the tutorial that I just showed you was made 2 years ago, and Nice Grid, the version of Nice Grid was Nice Grid 2. It did not handle quad-tree grids. However, we now have a version called Nice Grid 4, which does handle mixed grids. However, it will only change the nodes and elements that are the triangular elements and the associated nodes. So the quadrangular elements will remain fixed. So the quadrangular part of the grid will not be optimized. That version of Nice Grid 4, I don't think it's publicly available, but just send me an email and I'll send you the version of the code. I'd also like to mention that within OpenCoasts, you should use purely triangular grids. OpenCoasts does run mixed grids. However, the viewer can only handle triangles. So if you run a mixed grid in OpenCoasts, then you will not be able to see the results in the OpenCoasts viewer. You can, of course, download the results files from OpenCoasts and then view them in your own computer, but you cannot use our own viewer. Okay, are there any more questions? Okay, if not, okay, if there are no more questions, we'll adjourn. I don't know what's in the program for now. Annabella, it's up to you now.
Yes, thank you, Andre. Okay, everyone, this is the end of today's lectures. We are going to have more tomorrow, and then tomorrow we'll finish the users course, and then on Friday we'll have the developers course. So for tomorrow, here's the program, and what are we going to see? We are going to show you what is OpenCoasts and a little overview on forecast systems, and then to guide you through the use of OpenCoasts for the several options to generate 2D and 2D waves and currents forecasts, including a demo showing someone using the platform, and then to show you to use OpenCoasts to generate 3D forecasts. And finally, we are also going to show you the other parts of the OpenCoasts platform, how you can manage your forecasts and how you can see your results. At the end of tomorrow's course, we're also going to ask you to fill in a brief evaluation request so you can evaluate how well did we fare. That is very important for us, so we can improve next time. And that is all for today. If you have more questions, we are going to be around. So go ahead, say or ask anything you want. So all the lecture will be here for a while. And I hope to see all of you tomorrow. And I hope you enjoyed the course. And again, apologies for those slight problems in the beginning. Thank you.